Welcome to another lecture on principles of operating system. This will be our lecture 2, which will be dealing on computer systems and operating system structures. My name is Dr. Emmanuel Odoywood, and I am a computer engineering tutor, lecturer. Now, what we would be looking at will be computer system organization, to look at operational flow and hardware protection, system call and operating system services, storage architecture, operating system organization, operating system task, and virtual machines. Those are what we intend to cover in this course today. Now, this is how the computer system looks like. We have the CPU, which is your central processing system that helps to handle all the execution in the operating system. We have the disk controller, which handles and manages all the disks on your system. You could have your SSDs, or it could be your hard disk drive. That's the function of the disk controllers to handle. All right. Then you have your USB controllers. They are used for your USB controller allows you to interface your system with the output and input devices. For example, we have your mouse, your keyboard, your printer. They are all connected to the USB device. And then you also have your monitor, which we use to check what's happening while we are working on the system. And the monitor can be your flat screens, could be your LEDs and all that. So all these are tied to a graphics adapter, which helps you to see what needs to be done in that system. Now, we also have the memory, all right? Memory, the function of memory actually is to store all this information, right? So this was the idea of von Neumann. Von Neumann designed this idea for the first set of computers. And the way the computer works is that, let's look at the CPU execution. When there is an instruction that needs to be gotten, the CPU raises and fetch instruction at program counter. It tells the system to fetch instruction at program counter. So the system has to, the operating system has to, first of all, take that instruction and go down to fetch. Now, this is your program counter, which has all the data that you need in here. All the data that you need in here. This is your program counter. And it fetches that program counter. Once it does that, it now decodes the counter. In the process of decoding, it should be able to know where these instructions are stored in your working memory. Then it executes that instruction, possibly using registers. It will copy those instructions from your RAM up to your registers. And once it gets there, it does the execution. Then it writes results to memory or to registers, depending on what it was supposed to do. After that, it now resets the program counter PC to the next instruction. So that will now pull out another instruction. So it just keeps going on and on, keeps on repeating until finally you have a working program. That's just how it works. It starts from all these steps are what we call the fetch and execution, seen as FE cycles. Now, let's look at our I/O devices. The input-output devices do not handle process. The processing is done by the CPU. So we have several input-output devices. I is for input, O is for output. So we have the disk, the mouse, the keyboard, the printer, the monitor, and then more. You can have more devices. They are all our output devices. You have the scanner and all that. They are all output devices. I/O devices and the CPU execute concurrently, means that they can work together. There's a possibility that while you are printing stuff, you could also be working on Excel. Some calculations are going on. So the CPU is handling the spreadsheet calculations at the same time it's printing out for you. Each device controller is in charge of a particular device type. Now, each device controller has a local buffer, right? A buffer is a kind of a memory, little memory for storing some information that needs to be worked on. So each device has a local buffer, all right? The I/O is from the device to the local buffer of the controller. So if we are to get information here from the keyboard, it has a buffer. When you key in type in your keyboard, the buffer for the keyboard stores the information before it sends it down to be executed. All right. So CPU moves data from the main memory, all right, or to the main memory from the local buffers. Right. So the CPU moves data from main memory to the local buffers. It also moves data to the main memory from the local buffers. All right. So the CPU works with the local buffers are faster for the CPU to retrieve memory than actually waiting to get it straight from the hardware. Now we have interrupts. Interrupts transfers control to the interrupt service routine. All right. This is a way that the computer system can the operating system tends to tell the computer system to do certain things. Like if it's running a process, you could tell it stop the process, pick another process. All right. It could run what we call system calls. So interrupt service. So the interrupt service routine is segments of code that determine action to be taken from the interrupt. These are what you call interrupt. You have your interrupt numbers here, 0 down to 15 or more, and these are the addresses. So if there is anything, the operating system must service interrupts. So determining the type of interrupt, we have a polling interrupt, same interrupt handler called for all interrupts. In the polling system, the same interrupt handler is called for all interrupts. We then pose all the devices to figure out the reason for the interrupt. So once it gets the interrupt, it has to find out, it has to check all the hardware, which of them needs this my support. Then the second way of handling is it uses an interrupt vector table. Here you have different interrupt handlers will be executed for different interrupts. So at the end of the day, it's a handler that checks for certain levels of interrupts and tends to be faster. So instead of one interrupt handler handling all manner of interrupts, here you have different types of interrupts. So if it's a interrupt has to do with memory, the ones that will handle the memory will be activated. If it's for printers, the ones that handle outputs like printers will be activated. Now, operating system reserves the state of the CPU. It preserves the state of the CPU. It stores registers and the program counter or addresses of the interrupted instruction. The operating system stores the registers and the program counter. Now remember, it stores registers. Registers are storage locations and program counter. So it has to store all this information, addresses of interrupted instruction, so that it can get or fetch programs and execute them. Right? So whenever an interrupt pings or needs the operating system's attention, then the operating system must deal with it. It preserves the state of the CPU because by using interrupt, it can't just, the operating system may crash without the operating, and the system may crash without the operating system handling the interrupt properly, because there'll be so much demand from the on the CPU. So the operating system first has to store registers and programs and address of the interrupted instruction. So first of all, when the system needs to work, the CPU needs to work on a new system, the operating system will now say, store the old program and then load the new one. So you now have a situation where you have order, all right? It doesn't just allow them crash, there's order. So what happens to a new interrupt when the CPU is handling one interrupt? These are the processes that takes place. Incoming interrupts can be disabled while another interrupt is being processed. Incoming interrupt can be disabled while another process interrupt is incoming interrupts may be disabled while another interrupt is being processed. In this case, an incoming interrupt may be lost or may be buffered until they can be delivered. Have you seen it? So if it's coming, the work of the operating system, if it sees that it's not of high priority, it can disable it. All right, because I'm being handled. So there, in this case, you can have it being lost completely. It wasn't really look important, or it can be buffered, which means it can be stored and later delivered. Incoming interrupts can be masked. That's another way it handles it. Can be masked, ignored by the software completely. Then the third one is that incoming interrupts are delivered. They are delivered, but now they are delivered as they are lining up. So they are nested interrupts. They are lining up and then to be processed as they are being delivered, right? Now, one of the ways that can help the operating system, the computer system to function well is to create what we call direct memory access. So that it's not all the time that the memory has to, the main memory has to always to need help from the CPU. So direct memory access, DMA, is typically used for input-output devices with a lot of data to transfer in order to reduce the load on the CPU. So the device controller transfers blocks of data from buffer storage directly to the main memory without the CPU's intervention. The device controller interrupts CPU on completion of the I/O. It interrupts the CPU on completion of the input-output device, all right? So this is what happens here. You have the main memory here. You have the CPU. CPU must get things from main memory for it to work. You have the I/O devices here. If the I/O devices, imagine if the keyboard, each time you need to key in and you need to type on the keyboard, it has to come directly here. It's going to create problems. It means that it could be, CPU could be processing something else. There's only you, while you're typing the keyboard, it has to pause, leave that thing to watch your keyboard. So what happens is while you are typing on your keyboard, it sends it to the buffer here, right? And this is the DMA. Now, in the DMA, it waits. All you have typed are there. And then once it has seen that the CPU is a bit free, the operating system will now release all the typing, tell the CPU, print this on the screen. Then you have that done. So it reduces a lot of load, all right, from the CPU. Now let's look at process abstraction, which is another very important issue. One, a process is an instance of a program running with limited rights. An instance of a program running with limited rights. In fact, it is said that a process is a program in execution. Once you start programming, it starts running, it becomes a process, but it has limited rights. And it uses what we call address space. Now, the address space is a set of rights of a process, memory that the process can access. So all processes cannot access all memory locations. They have a limited memory location which they can access. And that is part of its process control block. It's always written on the process Yeah, on the program itself. So it knows where and where to access. Now, other permissions the process has are things like system calls. All right. So which system calls can it make? What files can it access? Those are some of the rights that it has. Now we have the process running. The process, remember, is a line of codes. So we have to protect the hardware from direct access to these lines of codes or to this code so they cannot break our system. All right. So there are some methods in which that is protected because we have to protect the operating system and also protect the application programs and the hardware. So we have what we call the CPU protection. Now to protect the CPU, we have dual mode operations and then we also have timer interrupts. Those are the two ways. Dual mode operation and timer interrupt. We'll see that how they function later. Then we also have memory protection techniques also, and then we also have I/O protection techniques. We're going to see all of them. Now, the question now is, should a process be able to execute any instruction? And the answer is no. The process should not be able to execute any instruction. For example, if you were to write a program and tell the process to get into my system and then shut down my keyboard, of course, that is a dangerous program. Or if you get into my system, copy things from my system and go, that's dangerous. You shouldn't be able to just write and go directly to the hardware and do something, right? So that has to be controlled. Because the problem is that it can alter system configuration. It can mess up with my system, alter the configuration. It can access unauthorized memory. It can access unauthorized keyboard, and etc. And that's what most viruses tend to do. So we have to prevent that. So how do we prevent that? Now, one is using the dual mode operation, as we had said earlier. The dual mode operation provides hardware support to differentiate between at least two modes of operation. One is the user mode, and one is the kernel mode. Now, in the user mode, the execution is done on behalf of the user. The execution is done on behalf of the user. So, the execution goes on, but the operating system is the one that monitors everything. All right, the operating system is the one that handles all the things that, and usually this is executed from application, all the apps. Okay, most apps, use utilize this. Okay, it helps to monitor all the things that they are doing. Right now, let's see. We have also the second one, which is the kernel mode. The kernel mode monitor supervisor. You can also call it monitor supervisor or system mode. All right, that's another way to look at it. The kernel mode, the execution is done on behalf of the operating system. Okay, it's done on behalf of the operating system. So we have a situation here where the kernel, when they're in kernel mode, there are direct accesses to the hardware from there. So usually the operating system that handles this kind of situations. Privileged instructions are only executable in the kernel mode. Yes. Executing privileged instructions in the user mode traps into the kernel mode. So things like print, when you want to use the screen or a printer, now the kernel has to take charge. All right. So it does not cause confusion because other devices are also using that. So even if your monitor says your software application asks someone to print a document, it has to be given, that instruction has to be given to the operating system. The operating system will now execute a privileged instruction for it to print or display things on your screen for you. Now let's look at how the dual mode kind of works. You have the mode bit added to the computer hardware to indicate the current mode. So if you launch your system, the operating system first and foremost, what happens is that your ROM loads its files and boosts your system and then hands over to the operating system to handle other things. So the operating system is given a kernel mode and it would indicate it could have a mode bit of 0 and then user could have a mode bit of 1. So when an interrupt or trap occurs, the hardware switches to the kernel mode. So usually, here's a situation where you have a program that is running, and then while the user program is executing, if something happens, if there's an interrupt or a fault, it traps to the kernel mode, because in kernel mode, we have most of the management systems all stored in the kernel. Operating system management systems are all stored in file management system, memory management systems. They are all stored in the kernel. So it's whatever fault traps down here. It says, look, help me. I need the file stored. And then when it finishes storing the file, it now sets back the operating system and says set user mode, keeps it back. Right? Allow the user. All right, allow the user to keep working. All right. So that is it. So the user needs something serious, like print a document. It sends it to kernel mode collects it, and then issues out the command for printing, and after that, now releases the user back to user mode to keep on working. So how do we prevent the process from executing indefinitely? Because a process can keep on going on, keep on processing until it finishes what it is doing. And that's dangerous for a CPU. It means other processes will not work if one process is super active without limit. So to prevent that, we use a timer. All right, time. A timer interrupts computer after specified period to ensure that the operating system maintains control. All right, it interrupts the computer after specified period to ensure that the operating system maintains control. The timer is decremented every clock tick. And when the timer reaches a value of 0, an interrupt automatically occurs. So if a process is running and has access to the CPU, the timer will be set immediately. The operating system automatically sets a timer on the CPU and says, look, you're going to run this process. Let's say it's going to run this process for 10 milliseconds. After 10 milliseconds, automatically that process will be pulled out. The operating system will raise an interrupt and say, look, stop this process and load a new one. So the CPU will stop that process, return it back into the working memory or back into the virtual memory, which we'll discuss later, and then automatically pick the new program and process it. And the timer is commonly used to implement time sharing, right? It's commonly used to implement time sharing. For example, we have operating systems that have only one CPU. And when they have only one CPU, they have to share it. In the process of sharing it, it has to be proprietary. So the timer is also used to compute the current time, right? Programming the timer can only be done in the kernel since it requires privileged instructions. Yes. The timer must talk to the hardware. It talks to the hardware. It's talking to the timer on your hard or your board. So it must have privileged instruction each time the timer being called. How do we isolate memory access? Okay, just the next one is memory management. How do we make sure that the processes do not jumble up and mix up together? There's a compartment for each process, because you can't just have all the processes just have one big system and then all of them are just reading all those things. It will be too much. So there has to be some management. And how that is done is using address space. It's a set of accessible addresses. You can see here, this is an address space here in this diagram. Process address spaces. You have from 0 up to max. So these are all address spaces. All right. So a big address space is, in this kind of situation, you can see it has been divided into different sectors where some parts store the stack, some store the heap, this one is storing the data, This one is storing the text. So, usually we have the virtual memory, which is usually in your hard drive. Okay, virtual memory is usually in the hard drive or in your solid state device. Okay. So we have the address space, which is a set of accessible addresses. As I've said earlier, for a 32-bit processor, there are 4 billion addresses. So between 0 and max, there are 4 billion addresses in this example here. Now, the virtual memory is a smart trick the computer uses when RAM gets full. When the RAM gets full. Now, the RAM is the working memory. It pretends that there is more RAM than there actually is by temporarily moving data you are not using from RAM to hard disk. So what happens here is there's an address space in RAM which the computer should store. Now there's a concept of virtual memory. Virtual memory is like a memory location that could be in your hard disk or solid state drive, all right, that is similar to the physical RAM. Now, the computer creates that environment so that it stores processes. And when a process needs to use the RAM, it comes forward and is used. If it needs to be backed up, it gets backed up in the virtual memory. So virtual memory could be created even within the RAM, because usually there's a hierarchy of memory. Memory moves from the RAM, the hard disk, the RAM, and then there's a cache. So it moves up that way. It's like a triangle. Okay, I'm going to draw something like a triangle. Then you have that. So here, the bottom part is secondary drive. The upper part is the solid state drive or hard drive. And here is the RAM. And finally, here is the cache. And here is the register. So we'll really go into detail much further as we go down. So when virtual memory is created at a lower memory position, like the hard drive or the RAM, and that memory is transferred in bits to the register. So anytime that the computer needs to pick something to work. Let's give an example like you have your desk that you used to read. Now you have your desk and then you have lots of books on your desk, piles of books on your desk, and you're here sitting down and reading. Now, if your desk is filled up with so many books, you won't have space to read. So at times, while you are reading, you now have a shelf somewhere here, which you move some books into that shelf so that you would have space here to read. So while you are reading, if you need a book, you go back to the shelf, pick it and bring it and read. When you don't need it again, you transfer it back here. Now that is an example of how the virtual memory works. The shelf creates something like a virtual memory where you store your backup of books you don't need, and then you bring it to the ones that you're currently reading to the desk. So that's how it works. So it pretends that there is more RAM than there actually is by temporarily moving data you are not using from RAM to the hard drive. Okay, it could be hard drive, or it could be your solid state device. Okay, this allows your computer to run big programs or many programs at once, even if the physical RAM is full. Okay, now let's look at the virtual memory here, how it works. Now, the virtual memory has a process layout. This is an example of, let's say, process layout of the virtual memory. And here it has lots of codes. It has data types that are heap, a stack, it has data, and it has code. This is similar to what a process is. But when you are storing that in the physical memory that is going to be used, where the computer wants to use, the physical memory could be your register, okay? Or it could be your RAM, all right? So it could be the register or it could be the RAM. So we have the code is stored here, data is stored here, heap is stored here, stack is stored here. Whatever else needs to be stored, other locations will be used to store elsewhere. So that is how it is. So it transfers something from the virtual address to physical memory. So definitely it must not, the virtual memory must not be the same address as physical memory. Just like you carry your books and put in the shelf to your table, they don't need to have exactly the same positioning. A book that is under does not have to always be under. It could be on top. Could have a stacked kind of memory. All right, let's say you have a stack kind of stuff. It means you are putting the one on top. You stack something, all right, and as you stack it, it gets in and then it gets out. So first in is the first out, like a stack. That is how the data they are storing in. But it could also be like a heap. Remember, in a heap, it is last in first out, LIFO. So that's it. So there are different methods in which you want to store that process over here. Okay, different methods. We will meet that as we go on more. Now let's look at providing the illusion of separate address spaces, like I explained earlier. You have the code, the data, the heap, and the stack. All these data are stored in several locations here. For example, here you have this code data or process 1. This is virtual address space 1. And then it passes through a translation map. Now, the translation map usually stores what we call a table that gives the actual location of whatever we're storing. Sometimes it's called a page table. We'll meet it as we go on in the course. And this table keeps tab of what is being stored here. So here we have code 2. These are all 2s, because this is these are all 1s. These are all 1s, not 2. Let me cancel this. These are all 1s. Now, all the 1s, you notice that you have stack 1 here, heap 1, code 1, and then you have data 1 here, which means they can be scattered all across board. You have, for process 2, you have data 2 up here, you have stack 2 here, heap 2 here, code 2 here. And if you have noticed what's happening, it doesn't matter where it keeps it on the physical memory. All it does is that if you load new translation map on switch, each time there is a new a process is moved from the virtual memory to the physical memory, automatically the map is being adjusted. So that's why you say load new translation map on switch. The map automatically is being upgraded to show the new location of these data. All right. Now we have kernel code, we have kernel data, and we have kernel heap and stacks. Remember, these are more of information that has to do with the operating system. So operating system is stored in the low memory folder here. So now the question we have is address translation and memory protection. How do we address all the locations so that despite the fact that they are scattered over, how do we make sure that one process does not have an issue with another process? So this is how it works. The processor issues its request for a virtual address. All right, the processor and the virtual address is gotten and is being checked. This translation address translation module checks. Is that virtual address available in the physical memory? If it's valid, then you have to find the physical memory here. If it's invalid, then you raise an exception and say no, It's not found. It's a problem. Now, if it's found, you now go and fetch the data, and that data is given to the processor to execute. That's just how it is. So it has a range in which it has to select. Now let's discuss memory protection. Memory protection. When a process is running, only one memory in that process, when a process is running, only memory in that process address space must be accessible. Only memory in that process address space must be accessible. That is one of the ways of protecting memory, to make sure that a process does not use more than its allocated memory location. So once the process is being fetched, when you fetch it and you need to execute, now during the fetch process, it must look at the PCB, process control block, look at where its instructions and data are from the instruction. So the instruction says where the data are, and the operating system goes there and fetches the data from that very memory location only. So it cannot execute outside, it cannot fetch instruction outside its own memory location. When executing in kernel mode, the kernel has unrestricted access to all memory. Unrestricted access into all memory. Now, another way, as I said earlier, we have what we call base and limits. All right. To provide memory protection, add two registers that determine the range of legal addresses a program may address. So we're going to add two registers, and the two registers are usually the base register and the limit register. So you have here the base register here and the limit register. The base register holds the smallest legal physical memory address. The smallest legal physical memory address. So we have an address here called 300040. That's the address. And then the limit contains the size of the range. And then the limit is here, and it says that the base register, it starts as 30040 and it moves a range of 120900. So you have the base, this is where it starts, and the limit is how long it is, and therefore where it should stop searching for that or picking data on that process. So it now knows in the address it's going to pick from 30040 up till 42090, and then that data is being fetched around that. So the data here is being fetched and being used to execute. Memory outside the defined range is therefore protected. So it's not going to pick anything up here, it's not going to pick anything down here, just within its range. And sometimes it's called base and bounds method. That's one of the ways of protecting memory, using base and bounds method. We look at the hardware protection, hardware address protection. Hardware address protection, we are looking at our CPU. Remember, we just gave an example how it goes to ensure that it picks something from the right place and brings it back. Similar to what we just did, the CPU just checks for the address, and when it says, there's the address I'm looking for, if the address is within the limit of this physical address, then yes. As far as it's less than the address within this stuff, so we look at it, yes, say okay, that this is between, let's say an example is 0 between previously we had, let's say we have something like 4 million, okay, 4,000, yeah. So you have to check if it's between 0 and 4,000, then definitely it says okay, yes, the base is right, it's between that range exists. All right, then now says look for the base plus limit. Is it there? It said yes, base and that limit exists. Then it finds what it was. So the load instructions for the base and limit registers are privileged instructions. They are privileged instructions, and they really exist in the kernel mode. All right. Virtual address translation using the base and bounds method. Now you have processor's view here, where you have the processor requesting virtual address from the memory. All right. So virtual address is within the memory. So that is how it has the limit, it has the base. It says it starts from here and ends here. So automatically it has the base and it has the bounds. When you implement that here, in implementation, it says the processor requests for the virtual memory within the base, looking for the base. And this is the base here. Is the base available within the same? Yes, it is. Therefore, it now asks for the bound. Is the bound within? Say yes, bound is within that environment. So we have here physical address comes here and it's looking for something between the base and the base plus bound. So if it's not, if the virtual address is greater than the bound, then you raise an exception. So you cannot allow it to cross to the next. It will not cross to this side. It has to be between here and here. So if it notices that there is, when it starts on the base and starts counting down, and the bound or the limit, as it was called before, is beyond the range of that memory location, then there's going to be an error. So that's how it protects the virtual address, and that's how it also protects the physical address. So whatever the physical address we have put here, if we come into the physical address and say that this physical address starts from 1000 and ends in 3000, it means there is a limit of 1000 at 1000, a limit of 2000. So it comes over there and also has to check 1000, limit of 2000. So even though we have this entire range, it knows that what it needs starts from here at the base and counts down to here. So what this exact stuff is, this exact from here to here, and this, what it needs here is just located within this place. So it duplicates exactly what's in virtual memory, physical memory. Now, the next one we're going to look at is IO protection, what we call input-output protection. How does the system protect input-output to ensure that all instructions are, the input-output instructions are done properly to devices that actually do exist and do not jump from one to another? So remember, we also said that IO's instructions are privileged instructions. So given the IO instructions are privileged, how do users perform input-output? We use what we call, users use system calls, because privileged instructions usually are handled by the operating system, remember. So your application places a system call, the app makes a system call on the OS, all right? So the method used by a process to request action by the operating system places a system call for a device, an IO device, and then the operating system goes and gets it. So a system call, the user code can issue a system call, which causes a trap. System call actually is a keyword that automatically tells the operating system to stop whatever it is doing and help it to bring a code. All right. So system call definitely can pause a process because the process needs something. So this operating system, the CPU will pause because of that demand by that process and tell the operating system to bring in what that process needs. So the user code can issue a system call which calls a trap. All right, causes a trap, and when there's a trap, the kernel handles the syscall. That is just it. So here we have a situation here where we have user process. The user process is executing, then it makes a system call system call. Automatically, this is within the user process. Automatically, the call makes the process to switch into kernel mode. From user mode, it has to pause and then switches into kernel mode. And within kernel mode, the operating system now has to look for that that instruction that the user process is looking for. So it causes a trap, turns the mode bit to 0, and then executes the same call. And once it does that, that's executed, it turns the bit back to 1. Remember, 0 is for kernel, 1 is for user mode, and then returns back and then continues processing. User mode, mode bit 1, kernel mode, mode bit 0. That is how the system call functions within the computer system, within the operating system or the computer system, from user process to kernel. Now, the system call has the interface between applications and the operating system, as I said earlier. User application here, the system call moves into the operating system in this direction. So the user application calls whatever it needs from the operating system, because the operating system is the only one that can operate within the kernel mode. Application uses an assembly instruction to trap into the kernel. Some high-level languages provide wrappers for system calls, all right? Like the C language provides wrappers for system calls. System calls pass parameters between an application and the operating system via registers or memory. Linux has about 300 system calls. We have for read, it has for write, it has for open, it has for close, it has for fork, it has for exec, it has for control and input-output controls and all that. IO control. So now read, once it says read, automatically wants to get input. It says write, means it wants to send out output. So automatically when it does, the system is running and this command execute, it has to, the operating system has to pause. Once the execute comes from an application program, it has to pause and execute this. So the operating system, whatever software you are building, incorporates the system calls in it. That's why you have to understand how the operating system works when you are building a software. Because while you are building a software, sometimes you need to talk to the system to give you an output, maybe check your screen or bring another file to run. And most of those times you have to read that file within, it could be within your module, but you need to be read. So the system call has to call those files, keep on calling those files for your sake to get the application running well. So you need to understand how the operating system works while you are coding. So that's what the real essence of, if you are in programming, coding, in any form, artificial intelligence, you need to understand how your operating system is actually working. So that when you write your code, you can write it for efficiency. Now we have the system services or system programs, right? They create a convenient environment for a program development and execution. You have command printers, command interpreters. That's an example of the system programs are within your operating system. Okay, they are there. You have your operating system. Sorry, you have the system program. Let's have a look at it. You have the system program that gets helps you to execute your applications, because first and foremost, whatever program you are using to write, you can use whatever language to write your application. And once you write the application and finish the app, you have the system program that does the interpretation, so that the operating system can understand what you're trying to say. Because the operating system will later send all that you're trying to say back to the hardware to execute. So you need to, while developing your program, your application, remember that there's a command interpreter. So when you install the application into your operating system, the command interpreter interprets what your operating system is saying, what the application is saying to the operating system. So it passes or executes other system programs. Like you have the system Windows management, and you have also system libraries. They are helping you. Those libraries and all that have system services within them. Let's look at now the command and interpreter system. The commands that are given to the operating system via command statements execute, all right? They run some things. Commands that are given to the operating system through command statements execute a lot of things. One is a process creation and deletion. Would have a process creation command, all right? So the compiler could here or create a process and it creates or delete a process. You have that for input-output handling. You have that for secondary storage management, all right? You have that for the main memory, you have that for the file systems access, and then you have the command interpreters that handle protection and networking and all that. So the interpreters must be able, whatever you are doing, whatever language you are writing, goes through the system programs, which your interpreter is there, or your compiler and interpreter is there, and interprets to the operating system for it to do the right thing. Then you have to obtain the next command and executes it. Programs that are read and interpreted control statements. Programs that read and interpret control statements are also called command line interpreter. All right. Programs that read and interpret control statements are also called command line interpreters. We have such shells. We have a Microsoft has PowerShell. In Unix, we have the shell. That's what we call in Unix. They read and interpret control statements within your application. We'll be looking at the storage structure of the computer system. Looking at the storage structure of the computer system. Now, as I said earlier, the computer system has memory that has to store information. One of them is the main memory, typically called the RAM, right? The RAM. Now, RAM, RAM, random access memory, is the only large storage media that the CPU can access directly. It's the large storage media that the CPU can access directly. All right. That's why it's called primary or main memory. But the secondary storage has large non-volatile storage capacity. Non-volatile. Memory is usually volatile. We know that. Secondary is non-volatile, such as the solid-state drive, which is use flash memory like your phone or USB stick. It has no moving parts, hence faster, quieter, and more durable. Then we have the magnetic disk. This is rigid metal or glass platters covered with magnetic recording materials. This is not as common as it used to be. Technology is moving more towards the solid-state drive. Then the disk surface is logically divided into tracks, subdivided into sectors, and the disk controller determines logical interaction between device and computer. So just like we have the disk controller, we also have the solid-state drive controllers also. They determine how the logical interaction between the device and the computer. So the storage systems are organized in a certain hierarchy based on speed, cost, volatility. Speed, cost, volatility. All right. Then let's look at the term. We are going to look at this concept of speed, cost, and volatility. How fast they are, how expensive they are, and how long they can store data. So look at the term caching. Caching is process of copying information into faster storage system. Process of copying information into faster storage system. The memory can be viewed as fast cache for secondary storage. It's a fast cache for secondary storage. That's why we also have registers that are also faster than the main memory. Now let's look at this. We have seen this. As I was explaining earlier, this is how the storage device hierarchy actually is. We have the registers at the top. These are the fastest. The cache followed by the cache, followed by the main memory, followed by the solid state disk. All right. So that's why you see the solid state disk is usually SSDs are much faster. They're much faster than the regular hard drive. You have your hard drive, you have the optical disk, and then you have your magnetic tapes. These were much in the older days, but they are still sometimes being used to store long-term data. So in terms of speed, we go up. This is faster. So in terms of speed, it's faster. All right. In terms of volatility, it also goes up V. So it's more volatile. This, whatever enters it can easily, once you shut down your power, this disappears, this disappears, this disappears. They need power to be available for it to store data. But at this level, you can pull out power, and this one down here will still store data. But these ones are very volatile. much volatile. And in terms of cost, this also is most expensive. Registers are more expensive, main memories are more expensive than hard disk, optical disk, and all that. So in terms of cost, speed, but when we go higher, it becomes more expensive, less time for storing data, and also faster. All right. But in terms of size, okay, when we come down, it gets larger. So as we come down here, this gets larger. All right. Now let's look at the task of the operating system. We had explained all these. Okay, I explained all these at introduction level at faster rate. But now, one of the tasks of the operating system is process management. Remember, process is a fundamental concept in operating system. A process is an instant of a program in execution. It's an instance of a process in execution. So when a program is in execution, we call it a process. Process needs resources. You need CPU time, memory, files, data, and I/O devices. The operating system is responsible for the following process management activities. One, for the creation of process and deletion of processes. That's what the operating system does. It handles process suspension and resumption. It handles process synchronization and inter-process communication. It handles process interaction, deadlock detection, avoidance, and correction. We will meet all this as we go on. Now, the main memory also is being managed by the operating system. So a second task is memory management. Main memory is an array of addressable words or bytes. Addressable words or bytes that is quickly accessible. The main memory is volatile, the RAM, as we had said earlier. The operating system is responsible for allocating and deallocating memory to the process, managing multiple processes within the memory. It keeps track of which parts of memory are used by which processes. It manages the sharing of memory between processes. So that's the memory. The operating system has to ensure that when a process demands for memory, it has to allocate. And once it's through with that memory, it deallocates that memory so that there will always be space for other processes to also use memory. And then there has to be, if there are multiple processes within memory, it must keep track of which part of memory are used and by which process, and then manage the sharing of the memory between those processes efficiently to ensure that processes do not clash into each other or they do not cause so many deadlocks or problems within the system. Determining which processes to load when memory becomes available is the job of the operating system also. Another task of the operating system is secondary storage and input-output management. Right? Since the primary storage, which is main memory, is expensive and volatile, secondary storage is required for backup. Always required for backup. The disk is the primary form of secondary storage. All right? We can call it the disk, the solid state disk, or we can call it the hard disk. All right? Whatever. OS performs storage allocation, free space management, etc. The I/O system or input-output system in the operating system consists of the device driver interface. All right? The device driver interface that abstracts device details. So the operating system in the I/O system is inside the operating system. It's one of the management module within the operating system. All right? The device driver interface abstracts device details. The drivers for specific until it handles its drivers for specific hardware devices. Okay. So these are some of the functions of the operating system, the storage, it handles the storage and all that. Another task of the operating system is file system. All right. File is a collection of related information. It presents programs and data. So the operating system is responsible for file creation and deletion, directory creation and deletion, supporting primitives of file directory manipulation, and mapping the files to disk in secondary storage. So the operating system is it has a lot of work to do. Make sure that you store your files, you create it. Just like when you go to your file and you just right click on it, and then you click on whatever you want to click on. You could have something like you could have new folder or new whatever, and it just creates it for you. And if you want to delete it, click on your delete button and it removes it. Another task is protection and security. That's another task that the operating system has to do. Protection mechanisms control access of processes to user and system resources. So the protection mechanism must distinguish between authorized and unauthorized use. Specify access controls to be imposed on use, and it must provide mechanisms for enforcement of access control. So the operating system must ensure that you must be authorized to use anything within the hardware. You can't allow the monitor is on and then one other program comes, switches off the monitor and decides to use it just without any control. You must be in charge. You must tell the operating system, I want to look at Microsoft Word, I want to look at PowerPoint, I want to look at this, and the operating system must give you that. If any other program comes in, it has to wait until the operating system gives it rights also. So let's look at how operating systems are organized. How are they organized? The older one, the simpler approach was when we had MS-DOS, things like MS-DOS. They provided a lot of functionality in little space, just little space. For example, here you look at it, it's not divided into modules, interfaces, and levels of functionality are not well separated. So you see all of them here. MS-DOS was just here. Application program stayed in the resident system program, and MS-DOS had handle device drivers. Then you had the ROM, BIOS, device drivers here. So what happened here was that the MS-DOS was just one simple operating system that was just handling all the functionalities. All the devices were installed into it. Device drivers were installed into it. Applications through the resident system program were all part of it. So it just kept in making it not to be very efficient. So we now moved on to the other ones. Okay, like an example here, we have the unique system structure. System structure, limiting structuring has two separate parts, system program. All right, here the kernel, within the kernel, everything below system call interface and above physical hardware were handled by the kernel. The file system, the CPU scheduling, and the memory management were all within here in the kernel. So that is what happened here. You have the users, shells and command compilers within the system program. The system call interface called was here and called into the main kernel of the operating system. So the main kernel of the operating system handled everything from file terminal handling, file system, CPU scheduling, everything was done here. And then those kernel interface to the hardware was around here, and then it talks to controllers, device controllers, and memory controllers. So the issue with this was that so many things were built into just one kernel. Just one kernel. So the kernel had to just switch between one task and the other. Then we also have the layered operating system structure, right? This is layered operating system structure. In this technique, the operating system is divided into a number of layers. The bottom layer is hardware, and the highest layer is the user interface. Each layer uses functions and services of only lower level layers. The operating system and the Linux kernel has successive layers of abstraction. So here you had in Linux, you have the user programs, talk to interface primitives, device drivers are here. Then you have the virtual memory layer, the I/O, the CPU scheduling, and then the hardware. So you can see that layer 0 up to layer N. Layer N, the outer layer, was the user program. So the user program had to interact with the interfaces, to the device drivers, and for the operating system to be able to work. So the operating system was the one coordinating every aspect of this device. Then we now move, let's look at monolithic versus microkernel operating systems. Monolithic operating systems have large kernels with a lot of components. They have a large kernel with a lot of components. For example, Linux, Windows, and Mac OS. They have a large kernel with a lot of components. Now remember that the kernel is the core of the operating system. The kernel is the core of the operating system, and it contains memory management, file management, process management, synchronization management. All the management are in the kernel. They are in the kernel. So for a monolithic, it means that everything is inside that kernel. Have a large kernel with a lot of components inside it. Now, microkernels moves as much from the kernel into user space. It moves as much from the kernel into user space. You have a small core operating system components running at kernel level, just a small core. The operating system services built from many independent user level processes. So the operating system services are built from many independent user level processes. So it moves some of the functions. For example, it could move memory management to a user level, or file management to a user level, so that some things can be done at the user level. It must not always come straight to the kernel before it works. All right, some systems allow that lightweight operating systems. So the communication between modules is with message passing. So each module within the operating system communicates using messages. The benefit is that it is easier to extend a microkernel. That's the benefit of microkernels. It's easier to extend it. It is easier to port operating system to new architectures. Microkernels can be ported to new architectures because it's just the core things of managing the hardware that it has to handle. Other ones can be handled elsewhere. It is more reliable and more secure. Less code is running in kernel mode. Just a lightweight code running in kernel mode. And whatever it needs is for the kernel to just tell another stuff in user mode that would have been in kernel mode to handle the thing. But the problem is that the performance overhead severe for naive implementation. The performance overhead is severe for naive implementation. That means that if you do not code well, not write your system code well, you may have a problem of how you get things done, because they're not all in one place, they are scattered all around. So you need to find a way to make your messages very clear and well linked so that you can make a system call and it works with ease. Because the system call is not really part of the kernel. Now let's look at how the microkernel looks here. We have a monolith kernel-based operating system. Like we said, the Windows is monolith. In this environment, you see here we have the system call from the application, gets into the system, and then it handles the inter-process communication, file system, scheduler, virtual memory, device, all the things are done by this big operating system so that it can talk to hardware. Now that's the size of the kernel. Remember, this is user mode up here, just this. Whereas here, when you come to this, you see the kernel is so small. Just basic inter-process communication, virtual memory, and scheduling is handled. Just 3 things. Then the device driver is handed over to the user. So at user mode, you can call your devices. You can create files and folders at user mode. All right. Even Unix server and that. Then application processes can communicate with each other at user mode. So once you are installing the system, the main kernel is very small. That is what microkernel based operating system operates. Okay. So we have this is the virtual machines. The operating system is like a virtual machine of the physical machine. Remember that it has applications passing through the operating system, communicating with the hardware. That's why it's seen like the operating system has all the components of the hardware. It has the CPU, processor management. So your CPU in hardware, it has something for it. It has memory management. So your memory, it manages it. It has your file system management, handles that also. It has your I/O device manager. So everything that is here within the hardware is also being managed. So all the components that are being managed in the hardware, the operating system has a module that handles it. So that's why it's usually called a virtual machine. So here's an example of virtual machine. We have virtual machine 1, 2, 3, which could be different operating systems. You have different operating systems being installed on a virtual machine monitor. That's why sometimes you have something, somebody can move from a network operating system to just a user operating system with ease. Right? That's just it. Now let's say this. So what are the use cases? Use case why we need to have multiple operating systems. One is because of resource configuration. That's why some machines you have multiple operating systems. You have resource configuration, running multiple operating systems, either the same or different operating systems. Sometimes run existing operating system binaries on different architecture. So that's something that what causes it. Somebody wants to run different operating system on one device because you're trying to maybe do different things at different times. So, all right. So we've been able to cover these computer system organization, the operational flow and hardware protection, system call and operating system services, storage architecture, operating system organization, OS task, and virtual machines within this course. So please, I would like you to all right, subscribe, share this so that others can also see and understand how the computer system is organized in connection with the operating system and why it is necessary to understand operating system as a computer expert, computer science, a programmer, a designer, or any expert in computer technology. All right, we'll meet on the next course. Have a good day.